Today's speakers are Eric McCarthy, Alessandro Coglio, and Eric Smith from the Kestrel Institute. They will discuss their work on developing and using tools and libraries for proving correctness of R1CS gadgets with respect to formal specifications. This work is particularly relevant for Tezos because last year we introduced sapling for privacy-preserving transactions. Sapling is a protocol that relies on elliptic curves and zero-knowledge proofs. And given that zero-knowledge proofs have a very peculiar cost model, the Electric Coin Company, the original designers of sapling, designed a new curve called JubJub to work efficiently with zero-knowledge proofs, a property that sometimes is called being ZK-friendly. Given that all this is a very new cryptography, formally verifying it seemed very appropriate, and that's the motivation for this work. Enough context for me. Feel free to ask any question directly on the chat, and a Q&A session will happen at the end of the presentation. Thank you, and let's start with the presentation.
Hello, everyone. My name is Eric McCarthy. I work at Kestrel Institute in Palo Alto, and together with my colleagues Alessandro, Coglio, and Eric Smith, we will describe some of the work we've been doing on formally verifying R1CS gadgets. Tezos has an admirable emphasis on formal verification. Tezos uses the sapling protocol for privacy-preserving transactions. The sapling protocol has been scrutinized by auditors, but as far as we know, it has not been previously formalized and verified in any theorem prover. It is good to make some progress towards that goal to increase the security for users of sapling. So in sapling, among other things, there are zero-knowledge proofs that use computations expressed as rank 1 constraint systems. Now we're going to explain more about rank 1 constraint systems later. They're mathematical structures unlike conventional programming languages. It's harder to write and analyze programs in R1CS. But we'll get into the details later. So sapling is documented in the Zcash protocol specification, along with theorems that support the correctness argument. So in this talk, we're going to be talking about formally specifying and verifying the theorems from the Zcash specification that support this, the R1CSs that implement and use JubJub curve operations and related gadgets. And our ultimate goal is to formally verify the entire spend and output R1CSs for sapling. So formal verification of R1CS in a theorem prover. So we need to specify and verify. It's laborious and error prone because the R1CS is large and not a conventional programming language. So a lot of the standard techniques do not apply. Tool support is needed. A theorem prover is a general purpose tool for formulating and proving logical assertions. All claims are checked by the machine. So we have high assurance, and theorem proving is a very good fit for formally verifying R1CSs. You can have a rich specification language that can capture any desired computation, can have other properties specified as well. Exhaustive testing is not feasible in this case, and we have powerful automated proof techniques. So we use a combination of the ACL2 Theorem Prover and Kestrel's X Theorem Prover built on top of ACL2, which has been specialized for R1CS reasoning. And here's just a overview of what goes into the prover. We have formal specifications and theorems. We have the R1CS, which is lifted up from the mathematical description, and we have libraries that help with everything. And then we prove the equivalence. So now I'm going to pass this off to Eric Smith.
Yeah, so we built in ACL2 a formal specification of prime fields, which underlie a lot of the R1CS machinery. So like many specs in ACL2, this is an executable specification, so we can take the functions and run them. But much more importantly, we can reason about the functions. We can prove theorems about the prime field operations that support all the R1CSs. For any prime P, we define the prime field as containing the integers starting at 0 and going up to P-1. And we define for these prime fields the standard operations: addition, subtraction, negation, multiplication, exponentiation, inversion, and division, all of which are taken modulo the prime. And then we prove many properties of these operations, some of which are sort of basic arithmetic properties that also hold for prime fields. And some of them actually do depend on the fact that P is a prime. Many rules also connect these prime field operations with equivalent but simpler operations phrased in terms of other vocabulary. So one of the things about R1CS is that you have to express everything in terms of prime field operations, but often you're really trying to do something a little bit different, or that you could phrase in a different way. So these rules that we prove in the theorem prover about the prime field operations help connect them to these other notions, which are what you're often trying to get at with the R1CS. Collectively, we have about 6,000 lines of definitions, theorems, and documentation in the library. And it is open source in the community libraries of the ACL2 Theorem Prover, and it has documentation in the manual for the ACL2 Theorem Prover.
Yeah, so on top of the prime field formalization that Eric just described, we built a formal specification of elliptic curves, also in the ACL2 Theorem Prover. We have a formalization of several kinds of curves. Particularly relevant here are twisted Edwards and Montgomery form of elliptic curves. There we have defined operations on these curves, such as group addition, scalar multiplication, and so on. And similarly to prime fields, we have proved theorems about these operations. It's sort of what you expect, the closure of group addition, commutativity, other properties like that. We also have in this library some proofs of theorems listed in the Zcash protocol specification, because they apply to elliptic curves in general, not just to JubJub. So that seemed like the right place to put them, is in this general elliptic curve library. Just to give you an idea of the size, the library currently consists of about over 11,000 lines of text, really. We're counting just with WC-L all the lines, including blank lines, but it's just to give you an idea of the size. There's definitions, there's theorems, there's documentation, and similarly to what Eric showed before, here we have a link for the code on GitHub, and then a link to the HTML manual pages generated from the documentation. Next, please. Here I'm going to just show you just a few little samples of certain parts of this library. We're not going to go into all the details, just to give an idea, to give a feeling for it. So you can see on the right, this is the mathematical definition of twisted Edwards group addition. So it's a formula that is well known. In the blue box on the left, you see the ACL2 formalization of that operation. Again, the details are not important here, but the one thing I wanted to point out is that the ACL2 definition explicates the dependency of this operation on the curve, because that's left implicit as often in the mathematical notation. But if you notice, the operation in ACL2 takes 3 arguments, 2 points and 1 curve. So curves are represented as sort of values, like data objects in the formalization. Next, please. So here's an example of a very simple theorem, which is commutativity of twisted Edwards addition. It just says that it's commutative, and this one, the theorem prover can prove it just completely automatically just by expanding the definition. That's a very simple proof. Next, please. Here is a slightly more elaborate proof. This just says that if P is a point of order R, then doing a scalar multiplication by K is the same as doing a scalar multiplication by K mod R, because it has a cyclicity there, right? This theorem is also not difficult to prove, but it requires a few hints from the user. Essentially, we have to tell the prover to expand K into sort of its quotient and remainder, the mod, and then after that, the simplification rules can kick in and can essentially get rid of the quotient part, and then the remainder part remains. That's how you prove this theorem. Next, please. Here's then on top, so after the prime fields, elliptic curves, and then on top of that, there is this formal specification of Zcash JubJub. This is based on the Zcash protocol specification. We took the relevant parts of it, the ones that have to do with the JubJub curve, and we formalize them in ACL2 in the Zcash library. So there's a definition of the JubJub curve in both Twisted Edwards and Montgomery form, theorems about it, and also importantly, there's the definition of Pedersen hash. It's a hash that uses elliptic curve operations on JubJub. There are some auxiliary definitions, and this one also has theorems. The theorems here serve two purposes. One is to validate the formal specification. That is true for pretty much every kind of formal specification. But the other one, very relevant here, is that some of the theorems support the correctness of the R1CS gadgets. And I'll show an example next. But before that, just again, to give you an idea of the size, this library currently is about 7,000 lines. Again, definitions, theorems, documentations, just lines of the file, and you can find the code and documentation and the links provided. Next, please. So here, just a list of the main theorems from the Zcash protocol specification that we have proved. I'm trying to use here essentially the same terminology used in the Zcash protocol specification. So there are certain injectivity properties, things about Pedersen hash, and so on. I'm not going to go into any detail here, but in the next slide, I'm going to just talk briefly about one interesting theorem. Next, please. Oh, sorry, before let me back up for a moment. Here's an example. Here's how next, please. Yeah, so here's how we formalize the JubJub curve in ACL2. So essentially, the curve is a data value that is defined by the prime number underlying the field, the A coefficient and the D coefficient. These are the known coefficients for Twisted Edwards curves. And we just taking on the right, you see the screenshot from the Zcash protocol specification, and you see the ACL2 equivalent on the left. Next, please. Here is an excerpt from definition of Pedersen hash. So again, on the right, there is the text from the Zcash protocol specification, in which part of Pedersen hash is to take a segment of bits, divide them into segments of 3 bits, and each segment of 3 bits gives rise to an integer, and that integer is scaled and added to the other integers for the other segments. And this construction actually has some interesting properties which we have proved as part of this work, because some of the correctness of the R1CS depend on these properties. And once again, on the left, you see the ACL2 formalization of that. Just one quick thing to note here is that there is you can see a summation in the Zcash protocol specification, the bottom line there, and that is formalized as a recursion in ACL2. That's often the case for this kind of theorem provers. Next, please. Here is something interesting. There is a theorem in Zcash specification which is about addition of points for Pedersen hash. So Pedersen hash is based on adding points on the JubJub curve. This could be done, functionally speaking, just on Twisted Edwards addition, using the Twisted Edwards addition formula. However, the Montgomery addition formula is more efficient in R1CS. And there are efficient ways to convert between Twisted Edwards and Montgomery point coordinates. So it's a birational mapping. That's a well-known thing. So what the R1CS do is convert Twisted Edwards to Montgomery, do additions in Montgomery, and then convert back to Twisted Edwards. So this all works well, but there is a very critical condition that must be satisfied, because while Twisted Edwards addition is a complete formula, it works on every point on the curve, the Montgomery formula, it only works if the points do not have the same x coordinate. If they do, you have to use a slightly different formula. It's a doubling formula for that. So what this Zcash theorem says is that no matter how you add the Pedersen points, they never have the same x coordinate. It's not a super difficult theorem, but it is a bit involved, and so that took a bit of work, to formalize and to prove in ACL2, and we actually had to use a different proof approach than the one in the Zcash specification, which is perfectly adequate there, but for ACL2 there was more like inductive approach that worked better. Next, please.
Yes, so we talked about R1CSs before, and now I'm going to talk a little more depth about what they are and how they work. So they're called rank 1 constraint systems, and in order to encode a computation for certain kinds of zero knowledge proofs, the computation must be represented as an R1CS. So it's a very strange representation of programs from a programming perspective. This is what you get. There's a large prime P, and all variables and constants represent elements of the prime field defined by P. So integers from 0 to P minus 1. There are no control constructs. The R1CS represents a conjunction of equality constraints over the variables, and the only operations allowed are addition and multiplication modulo P. Auxiliary variables can be introduced to store the results of subcomputations. And if you are trying to represent a function, which you typically do, you would need to designate certain variables as inputs and others as outputs. Next. So an R1CS with M constraints over N variables has this form. So if we just take a look at the first one, you can see there's a bunch of A's, a bunch of B's and C's. So we can say A term times B term equals C term. And the A's, B's, and C's, all of those coefficients are all constant field elements. And the V's are the N variables that range over field elements. The additions and multiplications are all prime field operations. Notice each constraint is roughly of the form, A times B equals C, but those are more like dot products of the A vector and the B vector. So in practice, each constraint only concerns a small number of variables. So we write them in a sparse format, as you'll see later. Slide. So R1CS gadgets, we call them, are constraints that realize a certain purpose. So that you can build a complex R1CS out of lots of small gadgets, which can build bigger gadgets and so forth. So when some of the typical gadgets you use to build your R1CS gadget, you decompose a number into bits. You can select an element by a sequence by an index. You can even calculate a hash function with a really big gadget. More precisely, an R1CS gadget may be a parameterized family. So a gadget to decompose the number into bits may be parameterized over the number of bits. You would generate a different R1CS for a different input to the gadget generator. They're usually generated programmatically. An example would be the Rust-Bellman library. While the design and generation process is hierarchically structured, the end result is essentially a flat collection of R1CS constraints. So this is appropriate for zero knowledge proofs, but it makes formal verification more difficult. We've been working on approaches to preserve the hierarchical structure. So we picked the example of a NAND gate gadget because it's the universal gate. You can build anything. So if you were looking at the R1CS constraints and wondering, well, how would I program something like that? Well, here's one way that just shows you can. It doesn't make it easy, but just taking a look at the NAND function here. If x and y are both 1, we return 0. Otherwise, we return 1. And if we look at the R1CS constraint, it's fairly clear that if you designate x and y as inputs and z as an output, this represents the same function. If you see x and y are both 1, then the left-hand side is 1, the right-hand side is 1, and z must be 0. If either x or y is 0, or both are 0, the left-hand side is 0, and 1 minus z must be 0, therefore z must be 1. And we assume that x and y are constrained elsewhere to be bits. Here's a selection gadget, like a relay. If b is 1, you return the field element x, otherwise y. So b, the bit, x and y, the field elements, are all inputs, and z is a field element output. And we can see the R1CS constraint that's equivalent to that. If b is 1, then y minus x equals y minus z. So we know that x must equal z. And therefore, the z returned is x. If b equals 0, then the left-hand side is 0, and the right-hand side must be 0, so y must equal z, or z must equal y. So that's how you encode. There's a couple examples of how you would encode simple functions into R1CS gadgets. So some of the issues with understanding R1CSs are they can be very large, tens of thousands of constraints, even nearly 100,000 in the case of the spend circuit. Flattening a large computation into an R1CS loses its structure, making it harder to understand. And people make gadgets very cleverly to express certain computations using prime field operations that are not very natural for people who are using conventional programming languages. Optimizations may be employed to reduce the number of constraints, which further obfuscates things. It may not be clear which variables are inputs and which are outputs if you're just looking at the data structure. Mysterious constants often appear and can depend on a large prime. So many powers of 2 especially for splitting into bits or recombining. The JubJub curve parameters such as d, 1 over d. I think there might be a square root in there somewhere. And for a given binding of values to the variables, you can easily test if the constraints are satisfied, but sometimes it's hard to show there are no other bindings of the input and output variables that satisfy the constraints. And we'll get into some of those details later. So, all in all, R1CSs are a very good target for formal methods.
So here are a couple of slides in which we are just trying to kind of frame the general problem of formal verification of R1CSs in general terms. So we're not going to discuss them in great detail, just to give a quick overview, but then you can read the slides in more detail at your leisure. Yes, so an R1CS mathematically defines a relation, a predicate, let's call it R, over the variables contained in R1CS, V1, V2, etc. Based on the purpose of the R1CS, so what it does, is it an AND gate, is it a bit constrainer, what is it? We can sort of naturally divide the variables into two disjoint sets. There are what we can call main variables and auxiliary variables. The main variables are really the ones that are relevant to describing the purpose of the gadget. For example, what are the inputs, what are the outputs? And those are the ones that are generally referenced by other R1CS constraints when this one described by R is used in a larger one, right? So it's sort of hierarchical composition. The auxiliary variables, their purpose is really just to relate the main variables together, because R1CS language is limited, and so you may need additional variables to say things that relate the main variables. Okay, so that's what an R1CS is. So a specification for an R1CS, we can think of it as another predicate, let's call it S, over the main variables that can be written in any language, any high-level formal language. Normally you would write it in, for example, in a theorem prover or something like that. So we can say, what does it mean for the R1CS to be correct with respect to the specification? We can formalize it like that. We can say that saying that S holds is equivalent to saying that R holds for some value of the auxiliary variables. Okay, just to be more precise, in general, as often happens with the software and things like that, these kind of equivalencies are predicated upon certain preconditions. So only under certain precondition, call it P, on the main variables, S should be equivalent to R, for some auxiliary variables. And so formally verifying R1CS means showing that the formula above is a theorem. We do that in the theorem prover. Next slide, please. Slide elaboration on top of that. So the correctness formula, it's copied from the previous slide, is S if and only if R for some auxiliary variables. You can divide the implication into two directions. One that we call the soundness, which says that every R1CS solution satisfies the specification. In this, the existential quantifier in the premise becomes essentially universal over the whole implication. The completeness property, that's the other direction of the implication, says that if something satisfies the specification, then there is in fact a solution to the R1CS that obtained by extending these values for the main variables to the values to the auxiliary variables. Often, a specification describes a functional computation, call it F, in which means that the specification S just says that the variables are divided into inputs and outputs, and the specification holds when the outputs are equal to F applied to the inputs. That's often the case here. That's it.
Okay, so we built a formalization of R1CSs in the ACL2 Theorem Prover. So first we define the syntax of an R1CS as just an ACL2 object, just a piece of data, specifically a three-tuple containing a prime, a list of variables, and most importantly, a list of constraints. Each constraint has those three vectors, A, B, and C, that we talked about before. And we represent these in sparse form. It turns out for big R1CSs, especially, almost all the coefficients are zero. So we had a dense form, but that was representing too many zeros. So now we have the sparse form where we omit anything whose coefficient is zero. So an example of a vector there, we have pairs of coefficients and values. So we have 7x plus 3y plus 12. And the things that get coefficients are either the variables or this special constant 1. So 1 times 12 gives us the additive 12 constant term. So given this syntax of R1CSs as data, we need to define the semantics. What does it mean for an R1CS to hold? And here we introduce the notion of evaluation, just an assignment of values to all the variables of the R1CS. That lets us talk about whether an R1CS holds over evaluation. And we say it holds simply if all the constraints hold. Then a constraint holds if you can take the A, B, and C vectors, evaluate them by looking up all the values of all the variables that they mentioned and plugging in, and then doing the addition and multiplication, mod the prime, and then checking that the evaluated A times the evaluated B equals the evaluated C. So that's how we give meaning to R1CSs and allow us to prove in the theorem prover that certain properties of them hold. This amounts to about 400 lines of definitions, theorems, and documentation, and is open source along with the rest of our work in the community libraries of the ACL2 prover. And there's also documentation. Okay, so formal verification of R1CSs with ACL2 and ACS. Small gadgets or small R1CSs can be verified directly with the ACL2 prover. But we found that larger ones often require our specialized ACS prover for R1CS. The largest thing we've ever verified with ACS that's in R1CS form has over 20,000 constraints and also over 20,000 variables. And in general, ACS scales better than ACL2 in several ways. It allows bigger proofs to happen more automatically. One caveat in this work is we've mostly focused on the soundness, as Alessandro mentioned, the soundness and completeness. We've mostly focused on the soundness claims that say things like every R1CS solution satisfies the specification. We think that's probably the more important of the two directions of the proof, and also sort of the more simple one to actually state and prove. But for some gadgets, we have shown also completeness, that everything satisfying the spec can in fact be extended to an R1CS solution by finding suitable values for the auxiliary variables. But this does sort of require you to exhibit often concrete terms that represent all the auxiliary variables. We actually have a trick that we can apply to let the prover help us find those terms by solving constraints. But so far, our focus has mostly been on soundness. So we use the ACS toolkit. This started out as my PhD work at Stanford in the mid-2000s. It's a general purpose software verification toolkit based on top of ACL2. So ACL2 is also a programming language in addition to being a prover. So ACS is actually written in the ACL2 language, and you can prove properties of ACS itself. Large pieces of the code have been proved to be type correct, for example. But it's part of our trusted base. It has several variants, one for originally JVM bytecode, another version for reasoning about x86 binaries, and most recently, a version of ACS for reasoning about R1CSs. One of the things that ACS does is lift programs into logical terms. So given a program, a piece of data, maybe it's an x86 binary, maybe it's an R1CS, turn that into a logical term about variables, essentially. For the R1CS, it's the conjunction of the constraints over the variables. ACS also contains high-performance rewriters, provers, equivalence checkers, and test generators. So having lifted programs into this logical form, we can do a lot of things. Prove properties, show that two programs are equal, show that a program is equal to a spec, find interesting inputs that cause certain behaviors, or show that no such inputs exist. A key innovation in all of this is ACS's compact representation of these terms. It would be most natural to represent the terms as simply operator trees, just the simple mathematical terms. But the problem we found, especially when dealing with crypto, is that there can be massive sharing of subtrees. So if you're doing a cryptographic computation in rounds, the expression for one round appears multiple times in the expression for the next round, and the representation blows up exponentially. We found that if we were to actually represent some of these computations as trees, they would be the size of the galaxy, for example. So we have to take advantage of the fact that there's sharing in the substructure, and often really massive sharing. So ACS uses directed acyclic graphs, where you represent each unique term only once, and everything that references it just points to that unique representation. ACS is open source in the community libraries of ACL2 again, and we have a web page that gives more information on it.
Yes, I'll go very briefly here. So how do we get these R1CS? R1CS are typically not written by hand. You don't want to write 20,000 constraints. So they're usually generated programmatically by libraries, often written in Rust somehow, such as the libruzcache library, which uses the Bellman library. So we like to thank the Zcash team who actually helped us starting these. So we created a fork of libruzcache, and we extended it to generate R1CSs in the ACL2 representation, and also to generate smaller gadgets than just the full span and output circuits. We also extended it to exploit the namespace feature of these libraries to create a tree structure hierarchical representation of these R1CSs, which we have found useful for to understand as humans when we look at these circuits to help us decide how to go about it, how to prove things. So we would like actually to turn that into an independently usable Rust crate at some point. There's some very preliminary code, very rough, at the URL indicated, and you can see some examples of the flat entry structure R1CS is at the second URL here. That's it.
So how do we actually verify an R1CS with ACS? Well, there are basically two steps. The first one is the lifting that I mentioned before. Take the R1CS, the piece of data that represents it, and lift it into this logical term, in this case, an ACS DAG, our compact structure shared term representation. So we have a tool, lift Zcash R1CS, which is just a thin wrapper around a more general tool, lift R1CS, that sets the prime to be the JubJub prime that Zcash uses. We give it the name. This is the name of a constant, A331 lifted. And we give it the variables and the constraints in the R1CS, and the tool builds this DAG that we can then reason about in the next step. In this case, the example is from one of the appendices of the Zcash protocol spec and has to do with checking whether points are on a curve. Lifting uses our semantics of R1CS, so we essentially form a term that says an arbitrary valuation satisfies this R1CS, but then we repeatedly and aggressively simplify that using the rewriter in such a way that we can simplify away all the R1CS machinery, all the things that map the checking over all the constraints and the compute the dot product and so forth. The result is essentially phrased only in terms of prime field operations. So you get a big conjunction of equalities of little computations of the variables involving addition and multiplication mod the prime. And this is represented as an AX-DAG, which we can then reason about in the next step. And this lifting is usually automatic, although you can, if you want, introduce simplification rules at this point. So the second step is to apply the AX prover for R1CS. So here we have a tool called Verify Zcash R1CS, which is a thin wrapper around the regular Verify R1CS. You give it the name of the lifted R1CS in DAG form, the thing we just created in the previous step. You give it the spec, in this case, a call of a function that checks whether this point is on the curve. You give it lists of rewrite rules to apply, and you give it tactics. And that's where most of the work is. The user formulates rules and lists tactics that help the prover to get the proof. What this does is it applies the R1CS prover to try to show that the spec always holds, assuming that the R1CS holds. Some of the tactics include the rewrite tactic, which applies simplification or rewrite rules. And these are used to replace the prime field operations that you have to phrase everything in terms of when you're in the R1CS world with these higher level constructs by recognizing sub-gadgets. You know, this is really an XOR of 2 bits, or this is really packing some bits into a larger value. This is really adding two integers, that, for example, that are packed from bits. So we have rules that can recognize these gadgets, and we actually have a growing library of them for new idioms and gadgets that we encounter. Each rule, by the way, is proved as a theorem in ACL2, so that you can add new rules to the system soundly. You prove that, okay, whenever I see this, it really means this, and then you add that to the list of names that you've supplied to the prover for it to use as it works. You can give a set of rules, or you can give a sequence of sets of rules. So, you know, apply all these rules until there's nothing more that can be done. For example, to maybe move terms to the other sides of equalities or something, and then apply this set, and then apply this set, and so on. And the goal of all this is essentially to solve the constraints. So very often you'll have a variable that is constrained to be equal to some expression over the older variables, but that equality may not be obvious in the form of the constraints. So you want to move things around and simplify things so that you actually have an equality of the variable. Then the next tactic, the substitution tactic, will use that equality to get rid of auxiliary variables. It will essentially replace any mention of the variable with its defining expression and then eliminate that variable from the proof. So you do this repeatedly for every auxiliary variable that you can, one after another, or actually we've optimized it to do several substitutions at once because it was taking too long to do them one at a time for these big proofs. Eliminating variables, auxiliary variables, and the result is essentially something that should be very equivalent to the spec. So you've eliminated the auxiliaries, now you have maybe that the outputs are equal to some function of the inputs, which is what your spec is trying to say. You've removed all the R1CS strangeness and proven that the R1CS actually is connected to the higher level and simpler specification. We also support the sequence tactic to apply a sequence of tactics in order, and the rep tactic to repeatedly apply a sequence of tactics. And actually the default tactic of the prover is repeatedly rewrite and substitute. So just some examples of Zcash R1CSs that we've verified using AX. Things like checking that points are on curves, the conversion that Alessandro mentioned between C.T. Edwards and Montgomery formalizations, and other things like that. All these proofs are open source, and we have some documentation of the process of how we go about this in greater detail that is also in the manual. Another approach that we've looked at is to verify gadget generators. Observe that an R1CS is, one particular piece of data that has things baked into it, like the names of the variables, but also other things. How many bits are you packing? What we like to do instead is to verify a family of these R1CSs. So what we do is define a function in ACL2 that takes the parameters of this parameterized family and generates a particular instance. And then we verify the generator. An example is the range check gadget. So this is a gadget to compare a packed vector of bit variables to a particular constant. And the gadget actually depends in a deep way on which constant you're comparing to. In fact, even the number of constraints can differ for different constants that you're comparing to. I'll talk about it in the next slide. But the idea is, we don't want to just have the gadget for this particular constant that we have in mind today. We want to verify this in general. So a tool that takes the constant, generates the gadget, and also has the proof that it's always correct. So we have verified gadget generators for Boolean check, conditional equality, selection, non-zero check, XOR, and NAND bits, bit packing, and range check. And those are open source as usual. Just a bit more about this range check gadget. It's sort of weird. The spec is very simple. If you have a group of n single bit variables, you want to pack them together into an integer and just constrain that to be less than or equal to some constant. It sounds almost trivial, but remember, we're in the R1CS world. So we have this very limited vocabulary. How do you express that if all you have is addition, multiplication, and equality? So on the right is an excerpt from the Zcash protocol spec that shows just the definition of the gadget. And it's quite complicated. It depends on where exactly in the constant the 1 bits lie. Groups of contiguous bits, whether there's a trailing sequence of ones and so forth. It's also complicated by the fact that we want this to be efficient, to use as few constraints as possible. So it's non-obvious that this gadget is correct. We have a verified generator for it. So we've written an ACL2 function that takes the constant and the names of all the variables you want to use and generates the gadget. And in the next slide, I'll talk about how we prove that generator. So on the right, again, from the Zcash protocol spec is the proof of the correctness of the gadget that they've described. And we've done an analogous proof within the ACL2 prover. So we've shown that for our gadget generator for range check, no matter how you call it, it always creates a correct gadget for that particular constant and for those variable names that you chose. Correct means that the gadget holds if and only if the spec holds. And this is actually quite involved. It was about 2,000 lines of ACL2. The proof is available open source at the link at the bottom. And it was surprising to me how difficult it is just to compare a value to a constant when it's a large constant that is on the order of the prime.
To wrap up, this work shows that it is feasible to perform formal verification of R1CSs in a theorem prover, post hoc verification, but especially when the specification is good and we have access to the source code, might be pretty hard to do without that. But we developed not only formal specifications and proofs, but also tools that can be applied, gadgets, generators, and everything you've talked about, Eric and Alessandro. And we are interested in applying our tools to more R1CS applications. The tools and artifacts are all open sourced with a liberal license for reuse, and we welcome feedback and opportunities for collaboration. Here are our email addresses and our URL. And thank you. We'd like to thank the Tezos Foundation and Nomadic Labs and many others for making this work possible. Thank you very much for your time.
Thanks, everyone.
Thank you.
All right, waiting for everybody to connect. Okay, thanks for the presentation. It was very, very interesting. So let's have a look if there are any questions in the chat. If not, I do have a bunch of questions. So, okay, well, I can start while people think. So about one of the last parts of the presentation, you were saying you actually went the way of verifying a gadget generator rather than directly the constraint system. So basically you were, so the ground truth is the constraint system. So you were generating, you verify the function, you generate the constraint system, and you make sure that it's the same that is generated by Bellman. Is that what you, was that the approach?
We haven't actually finished that last step. We still are working on connecting up. Here's the generator. We can generate essentially the same gadget, but that adding it into the prover in a way that will connect it to the particular R1CS as a piece of data. I think that'll be working in probably a week or two, and that also allows us to just do it for sub gadgets. So you might imagine that the prover can do most of the proof, but there's this one weird sub gadget. So you go off and you use the gadget generator approach for that and plug in that proof into the larger proof. That's something we don't have working yet, but should be working soon.
Okay. And sorry, maybe I missed this along the presentation, but can you maybe recap what is the trusted computed base in your system? So what is that as a reviewer I should really look with attention, and what is that I could just push a button and and
Yeah.
wait for the result.
So you have to trust the ACL2 prover, the ACE prover, assuming you're using ACE and not just ACL2 itself. You should review our models, like have we correctly captured the specification, of the gadget? Have we correctly captured the semantics of R1CS? I think that's the main thing. I mean, you could worry about a cosmic ray coming and hitting your
Sure.
computer, of course. There's a Lisp runtime underneath ACL2 that you have to trust. Am I forgetting anything, guys?
Now, one thing you don't have to sort of trust are the proofs. You should trust the prover. So you don't need to review the proof hints, the lemmas. You don't even. One other thing you need to check is whether the formulation of the theorem, the top level theorems, captures the right thing that you want to prove.
Yeah, sure. That's the specification as usual. So, but all the proofs, all the tactics, all that, I don't need to.
Yeah, that's right. Yeah.
Okay. All right. So this work has been very, very specific. So it was very following Zcash and a particular technology, a particular R1CS. So given that you also have experiences in other, in other fields, how much of this work was novel to you? How much new technique you had to develop, and how much you could reuse from the existing work on programming languages verification, for example?
Yeah, one nice thing was that we already had the ACE prover. It's actually a prover generator that you can customize to various problems. And so it wasn't like we had to write a whole new prover from scratch. I think that sort of helps in the trust story. What we did do a lot of in this project is optimize. It turns out that the substitution was doing one variable at a time. If you have many variables, that's just too slow. And so we actually, on this and other blockchain projects where we were dealing with R1CS, we actually put a lot of engineering into optimizing the prover, but not so much building a whole new one. So that was nice. We did have to build the models of R1CS and prime fields to underlie it to support this style of proving. What do you guys think about this?
Yeah, I think it's accurate.
Well, I think we could talk about PFCS a little bit, Alessandro.
Yeah.
Okay, sure. Yeah. So just very briefly. So one issue with R1CS is that they are a completely flat list of constraints. But as we well know, there is a natural hierarchy when they are constructed, which you sort of think of them as modules that you construct. So one thing that we have built, we haven't used it much yet, but it's this notion that we call PFCS, which stands for prime field constraint system. It's sort of meant to be a generalization of R1CS, and the idea is that you can use essentially arbitrary expressions over prime fields, not just linear polynomial times linear polynomial equals linear polynomial as in R1CS. And also you can give names to, you can collect lists of these more general constraints into collection that you give names to them, and you have parameters so that you have essentially, they are kind of like, each one is a predicate, and then you can, another predicate can reference another predicate and can call it. So that's a way to keep the hierarchical structure. For those, then there's also the issue that we have done for some of them, built some PFCS generators because they're also parameterized. So that seems fairly promising, although, as I said, we haven't really used that much yet.
We think those might work okay for proving things about Starks or Planck.
I see. That's interesting.
Yeah, let me just say something more. You can have within PFCS, you can then have sort of restrictions to them, like that can map them to R1CS or to Planck or to other systems. So you can use that as a framework to reason and then maybe transform them. That's the other thing we want to look at, doing program transformations on R1CS or PFCS. Sort of this idea of refinement from formal specification.
I see. So I would really like to go into that, but there are a lot of questions. So let's see. So Mark is asking, are you aware of other projects doing formal verification on snark languages? And there were some answers in the chat, so I'm going to mention that, and then you can see if you know something else. So Bas Peters is mentioning work in EasyCrypt and Isabel and Koch on ZK proofs, and ZK Crypt and Pinocchio Q, and some work on Stark in Lean. So is there anything else you would like to mention, or?
Nothing else comes to mind. Yeah, I've heard about some of those. We haven't looked in great detail yet, but yeah, sure. I'm sure there's some ideas that can be cross-borrowed there. So yeah.
All right. So the next question is always from Mark. R1CS has unlimited fan-in gates, which is not the case for other snark-related constraint system. Did that influence your verification strategy?
I don't think it influenced it much. I mean, we are concerned in general about the size of these things, and that's why we use the axe prover. And once you start substituting, you start getting this explosion if the terms had been trees instead of DAGs. I think that might happen even with similar systems that don't have the unlimited fan-in.
Okay. So actually, the one problem of that we're having with Plonk is the fact that you're much more limited in the fan-in of your gates, so you end up having many more constraints. So the system tend to explode in size to deal with the same. Or I mean, at least if you're not careful. So Raphael is asking, have you been looking at more general project than Zcash, such as some comprising the ZK proof standardization?
We have looked at, yeah, actually, yes, other projects. For example, we worked on Ethereum semaphore in a different project. We also did some work on Helios Snark VM and yeah, in general, we are interested in trying other things. Eric, you guys want to say more?
No, I think you covered it. Yeah.
Yeah, we have this toolkit now, and we're interested in other applications of it and extensions to it. We think it's a set of powerful tools, and we have this growing library of verified gadgets that we're adding to as we see different idioms come across, and we think it could add a lot of value to new applications.
Okay, there is another question from Bas Peters. How much would your work simplify when starting from a clean slate implementation? That's the usual dream of a verification person.
Well, let me go ahead, Eric. Go ahead.
I'll just quickly note that one view could be that essentially all you would need might be a verified gadget generator. If you're not getting the R1CS from someone else over the transom and having to verify that particular thing, you could do the whole thing as a verified generator, potentially.
Yeah. Yeah, so we're working on a Plonk language, a small DSL to generate Plonk circuits, and yeah, being able to start from scratch and prove equivalence with the program directly, it's definitely simplify your life. So Miguel Ambrona is asking, you have mentioned the importance of verifying soundness over completeness of the CS. I agree with you that soundness is crucial. What problem can arise if completeness is not verified? Should a successful prover worry about the system not having been verified to be complete?
Well, for a specific zero knowledge proof, you need to have a witness as well as the R1CS. And if the witness does not work, if it's not complete and the witness doesn't work, well, you're not going to be able to generate the proof, right? So it's not a problem for the verifier of the proof in the ZK system. It's just a problem for the one who generates it. So if you're going to automate generation of the proofs in a complete way, then it's a problem. But in most zero knowledge proofs, you'll find out when you're trying to say, well, I spent this money or whatever, it's going to fail and you're going to have to generate a new key or something. So usually completeness isn't the biggest worry.
Yeah,
Okay.
and let me say something. Yeah, and no, I'm not at all an expert in this, so this may not be quite. But my understanding is that what may happen is that perhaps, let's say, you have a perfectly good transaction you want to create a zero-knowledge proof of, but if somehow completeness doesn't hold, then you may be unable to produce a valid proof. I think that's just sort of what Eric said, but I rephrase it in a concrete term. But again, I really defer to the real experts in zero-knowledge proofs here, who maybe can,
You just might not be able to do that particular transaction. You may need to generate a new nonce or something and generate a different.
Something. Mm-hmm. Yeah, I think definitely we want to have completeness, eventually. It just has been not initial.
At least you want to know what your preconditions are, right? You want to know where you divide by 0 in the circuit, or where you have constraints that can't be satisfied.
Okay, so maybe last question to wrap up, which is connected to one of the previous questions. How much of this work do you think can be reused for next projects? And in particular, maybe if you can say a word about Plonk, which is getting more popular and is closer to home now.
I think nearly all of it can be reused. I mean, really just the model of R1CS versus the model of Plonk, and there's still, things that can be shared there as well.
Yeah, one of the
libraries, the tools. I don't know. Go ahead, Eric.
I was going to say one of the design goals for Axe all along has been to try to use a general purpose tool that you program by adding different rules and different sets of rules to it, so that you don't have to write a new prover for each specific application. You write one prover, and then all the rules are proven as small ACL2 theorems. So you can add and subtract rules and change things around. Compare this to a prover where all the simplifications are hand-coded. And now you want a new one, but you're worried that you're going to compromise the correctness of the whole thing by adding this new simplification. No, we prove it as a theorem in ACL2, and we say just use this one along with all the other ones that you're using.
Okay, so I think we're done with the questions. I think we can thank you again for your work and for your presentation and for the time to explain it.
Thank you. Thank you for your support.
Yeah.
Bye-bye.